Welcome to the second video on the construction of Iter integrals. So we have already defined the Iter integral for simple functions. And we have seen that it's actually the corresponding integration operator is an Iter isometry. Is an isometry thanks to Ito's isometry. So there's the hope that we can extend this continuous operator to a wider class of integrants. And this is the purpose of this video so the next step is extension of the integration operator or Iter integration operator operator I to a wider class of integrants. All right. Okay, so first thing I would like to do in this video is to define for you what I mean by wider class. So what our potential class of integrants will be. This is definition 3.3. Okay, first we need to fix some measurability. So f, which is our integrand, maps from the sample space omega and the time interval 0 to t to Rd is called measurable if f is what we work here on the product space, so we want that it's product measurable. So we take the sigma algebra on the probability space and look at the product sigma algebra with respect to the Borel sigma algebra. Measurable. So if you say as the function is measurable, we refer to this type of measurability. And f is called adapted. This is as before, so just as a reminder, so we have defined adapted, what adapted means for a stochastic process, and this is exactly what we mean here as well. So if I look at f at time t, this is supposed to be ft measurable for all. Right? This is exactly the adaptedness we have seen before. This is just to make the wording a bit shorter. So measurable means what you expect. You have a function defined on the product space, so it has to be measurable with respect to the filtration, with the sigma algebra on this product space. This is just what measurable here says. And adaptedness means, well, as before, we just want that it's at time t, f is ft measurable. Okay, so that's not very new. And the space I would like to consider now is basically all adapted functions f, all measurable and adapted functions, which are L2 integral. So this is my space H2 is defined as all f from this product space omega 0 to t to R, such that f is measurable, adapted, and we have that the L2 norm on this space H2, which I just write down here, is finite. Okay. And well, just small remark. So H2 is of course again considered as a subspace of all functions in L2 on this product space here. And this is the Lebesgue measure. Okay, so if you're very precise. This means we consider H2, which are actually equivalent classes of functions, right? Because this is the norm. We want that this is a norm, so we have actually not a function, we have an equivalent class of functions, and we can always find a representative which is indeed measurable and adapted and fulfills this condition. So the usual thing about L2 spaces, which you learned in analysis, also apply here. Okay. And now let's come to the main proposition of this video, which is Preposition 3.5, which tells you, well, if you have a function which is in H2, then there exists a sequence of simple functions, so Fn, which are supposed to be in H2 0, such that the simple function approximate in the H2 norm the given function f. Okay. So this, I mean, in short, this means H2 is dense in H2. Sorry, H2 0 is dense in H2. Okay. So this is a bit of a technical proof, but we have to go through it in order to be able to extend this ether integral here to this natural class of integrants given by the space H2. Okay, so let's go through the proof. Okay, proof. Step 1. So we do it in 4 steps in order to give him a bit more structure. So first step is without loss of generality, we might assume that we can assume f is bounded and adapted. So the main point being here bounded. Right, so this is the usual trick. So that's where we have to work for. Okay. So why is this enough to assume that my function f is bounded? Well, we can just always set introduce an approximating sequence fn, which is just saying, okay, if I'm less than minus n, I take the maximum of f with f, and if I'm getting bigger than n, then I'm cutting it off, so I take the minimum with n, and n is a natural number. So this just means I cut off my function if I'm hitting the level n or the level minus n. So my function is immediately bounded by the natural number n. And then by dominated convergence, my dominated convergence theorem here, it tells me, okay, of course, fn goes pointwise to f. So what I have here is that fn goes to f in H2 if n goes to infinity. Okay, and what we have, note fn is bounded as we wanted to have it, measurable, and adapted. For all n. Okay. So if we can approximate any function which is bounded, we can then extend it to any other function as well. Okay. So second step. My second claim is basically it's enough to approximate continuous functions f. So there exists a sequence fn. Right, I mean, this is not the fn again, it's just a general sequence of fn of bounded, measurable, adapted, and continuous functions. Fulfill the property that they approximate my f in H2. Right? So the only issue which I have to be careful here is fn might not be simple. So this is the second step is telling me well, if I can approximate every function in Hn with continuous functions. And this is good because then in the next step I only need to show that I can approximate continuous and bounded functions. Okay. How do I get this? Well, what do I want here? Okay, I want to define my sequence fn. So for t and n and n, we define fn to be the n times the integral from t minus 1 over n plus everything is well defined. So we just want to make so this x plus, I mean this plus notion just means I take always the maximum of x and 0. So I just to make everything well defined, and then I integrate from t minus n up to t and the function s. So what I do is I integrate over small instances, and you note here this normalizing factor is nothing else than 1 over t minus t over n. Now, so I integrate the function f over a small interval, and then I divide by the length of the interval, which by the fundamental theorem calculus will converge to the function f. And it's a continuous function because I integrate it. Okay. So what do we observe here? Go back to. So fn is bounded. Why is fn bounded? Because, well, we assumed in the first step that it's enough to assume that f is bounded, and then fn is bounded as well. That's good. Okay, we are measurable. Integration is not destroying this one. We are still adapted. Okay, and we are continuous. Right, because but of course we're not simple. I mean, this is not simple. In general, at least not simple. But not simple. Okay. That's good. So and now we need to understand why these fn approximate in H to the function f. But the good news is, okay, as how we constructed is the usual way to approximate function in L2 or any LP space. So with the continuous function, you can always, continuous function are dense in L2 spaces. So this is what we do here in the standard trick. And we know that we have pointwise convergence by the fundamental theorem of calculus. Then we can use dominated conversion to get the H2 conversion. Okay, so this was just, let me write down the argument which I just defined. So for every omega, we said, okay, first introduce the set A, which is the set of all on the product space of all omega and T, such that this Fn do not converge to F. And omega A omega is just all T in interval such that omega is in A. Oh. Okay. So, but now by the fundamental theorem of calculus, we know that for omega and omega, we have that the Lebesgue measure of A omega is 0, right? Because this is how we constructed them, right? And so these, for a fixed omega, this Fn will converge to F. Okay, and this means if you look at the product measure of A, this is 0. And now we use dominated convergence. Dominated conversion theorem. And we have that Fn also converges in F to 0. All right. Okay. So it's basically, it's what we see here. It's enough to consider bounded, to approximate bounded and continuous function. Okay, step 3. So we want to show that if I look at the limit h to going to 0 of the expected value of the integral to t, and then I look at the difference, or so I integrate over the difference of f and at time t and f at time t minus h, and now I need to be careful again to have everything well defined. So I take the minimum with the 0. Then I look at the L2 norm. Right, this goes to 0. Okay. Indeed. Taking Fn as in step 2. What do we get? So let's start calculate this expected value from over the integral from 0 to t of my difference. Okay. So this is what we want to calculate. And okay, well, let's talk about norms. So let's make here. I mean, it doesn't matter actually. Okay, if you show the one is going to 0, the other thing is going to 0 as well. Fine. Okay. So I just normalize it in order to have a norm, because then I can sneak in here my Fn. So I want to sneak in here the Fn approximation. Okay, so I get the H2 norm of the difference of F and Fn plus H2 norm of Fn plus minus f right. Wait, okay, here 2 dt and half. And last thing, which I forgot, okay, my fn at time t minus fn at time th at t minus h to the power 2 dt. Okay. That's so what I did, I inserted here fn at time t, then I minus plus fn. So the usual trick that you minus h minus plus h. Right? And this is what I spelled out here using the triangle inequality. And this is nothing else than triangle. Inequality. All right. Okay, now and then this section is hard to estimate, right? So what do we get? Okay, we have the first term. This is the first term is fine. N minus. And what I mean by fine is, I mean, this term goes to 0. If n goes to infinity. Yeah. Okay. Second term. Okay, we have here basically again the second time the difference of f and fn in the h2 norm, plus we have this constancy term at the point null. So at the over length of the interval h, we have here fn at time 0, and then f at time 0. Right? So this is, of course, I have here this little plus where I need to be careful. But this doesn't, I mean, doesn't harm us. So this goes to 0 as h goes to 0. Right? I mean, the second term here is bounded, and if h goes to 0, the product with h will go to 0 as well. Okay, that's good. So last term. Okay, well, that's not hard. Okay, let's copy it. Right. Now here you have, I mean, the h fn's are continuous, and you evaluate the function only with the difference of h. I mean, here at time t and here at time t minus h. So if h goes small, this will go to 0 as well. That's great. So what do we have here? As you hope for, this goes to 0 by dominated convergence. Convergent theory, plus using the continuity of h is continuous. Okay. So what we get here is this goes to 0 as h goes to 0 and n goes to infinity. Cool. Which gives us the claim, because, well, we can choose n as we want to. Okay, wait. So, I mean, we use, just to write it down as well, so we use step 2. Right, this hn, I mean, this here is where you use step 2. Okay, I should write it in gray as well. By step 2. All right. Okay, last step. Step 4. The claim is that there exists. I mean, this is the claim of the preposition is there exists actually a simple sequence which approximates f in H2 as n goes to infinity. Okay. So, just to recall, remind you, so by step 1 and step 2, it is sufficient to assume f is continuous and bounded. Okay. So let's do it. I mean, this continuous makes our life much easier because now we can use point-wise evaluations. So let's use the phi, which is fin, which is just a function from the real numbers to the geodetic points. So these are the geodetic points in R. Wire the function u, and what you do is you always look at the smaller geodetic point given a function point u. Okay. Yeah. So just let me draw you a picture. So if you're somewhere between J1 and right, this has two neighboring geodetic points, and your u is here, then phi n of u is just the next smaller geodetic number, right? It looks fancy, it's very simple. Okay. Define, and now we define our simple sequence for an S, 0 and t, 0 and 1, and n a natural number. We define f as fns omega t just to be f, and then s t t. Here we need to plus in order to have everything again well defined. Omega and omega, and t in our interval 0 to t. Right? So, okay, I mean, we need to find the right S, so this is what we have to do. So we basically define a class of possible approximation doing the job, and they're all simple, all right? Because what you do is, I mean, okay, this is a continuous function, so pointwise evaluations are fine. And now what you always do is you take a point S and then you look at the difference. So basically you move your t a bit by a number between 0 and 1, and then you look at the geodetic points. So between the two geodetic points, I mean, this is, or shifted geodetic points, this is constant. Okay, so I mean, this plus S, I mean, means basically you shift the geodetic points by S. Okay. So note. If you look at this here, S plus phi n of t minus s, well, this is always less than t, right? What you might end up bit small, being a bit smaller than 0. So this is why this plus here is coming from. But in the limit, I mean, you only need to have to define function be bigger than 0. And fns is in H2, right? Because we are constant between two duadic points for every s in 0 to t. But we need, okay, we need to find the right s. Moreover, what do we have? Well, if we look at the expected value of the integral 0 to t and then 0 to 1 of fns t minus f ds dt. Well, let's plug in the definition of fns to see what we get here. No. So this is just the definition from above here. S dt. Okay. Now, okay, we remind ourselves that, okay, this is a simple function which is constant between two duadic levels plus s. So what we get here is we sum over the duadic levels, j and z, of there is an integral, and now, okay, if we are between t and j minus j to the power n, j divided by 2 to the power n, and then t minus j minus 1 divided by the power n, and now we have also the intersection with 1. We just have here f at time s plus, right? So we are plugging in the definition of phi n, t 0 s dt. Okay, and now let's calculate. Okay, I mean, okay, let's forget the plus here. So what do we get? Right. Okay, I want to make a substitution. So wait, we introduce here the substitution. So I want to have this to be, so this is my substitution. Substitution as t minus 2 to the power minus n, because then we can make the substitution here. The factor and the summons, I mean, so this is the number of summons in the sum here. And then we get, from the substitution, we get another factor, which is 2 to the power minus n, right? This is coming from here. Then we have the integral from 0 to t, 0 to 1, of, this is just another Fubini, t and h minus t ds dh. Oh, this is not, the s is gone, sorry. Right. All right. And okay. Here we actually know this goes to 0 as n goes to infinity by step 3. And this is what we showed, right? We have shown it for general H, but I mean, this is still an H. So this means overall this goes to 0 as n goes right, because this constant here is compensated by this factor. That's fine. So this goes overall to 0. Right? This is here another Fubini. Okay. Cool. So what do you get? This means they exist. The subsequence such that if I look at the function from omega s to t to f and s, omega t converges to f of omega t p omega lambda, Lebesgue, right? This is the Lebesgue measure on 0, 1, and this is the Lebesgue measure on 0t. Almost surely. Okay. And now this implies, by Fubini, that they exist as 0, 0, 1, such that f, so if I fix this almost surely conversion subsequence, right? You have shown the conversions in an L2 space, so we have a conversion in a probability, okay, in measure here, and this means we can find a subsequence which converges almost surely, and then we can fix omega and S0 such that it converges on the smaller space for almost p. Oh, this is as k, so this k goes to infinity. P the lambda, so almost surely. And now, since everything is bounded, so by dominated convergence, we also know that this subsequence of f and k at the point S0 converges in H2 to f as it converges pointwise and is dominated by a constant k going to. All right, and this is actually our simple strategy. Okay, well, this is good enough, right? We just know that there exists a sequence that does the job. Okay. Okay, cool. So what have we learned here? So let me change the color. Let's go to the next page. So what we know now, let me give you a small summary. Okay, we know H to 0, so the simple functions are dense in the adapted 1 to L2 functions are dense. This is proposition 3.5. And we know that if I look at the integral operator I from H to 0 to L2 is a continuous operator. This was the contents of lemma 3.2. Hence, there exists a continuous extension of I from H from the simple functions to the L2 functions, right? how does it define? So if I look now of I from H2 to L2, I just take my definition to be, okay, approximate. I take it as the limit of an approximating sequence Fn. That's right. So where the convergence here, convergence of Fn takes place in L2, right? Because this is our random variables in L2 for any approximating sequence, for any sequence Fn, which is part of the simple functions, right? And this always exists here by the density, so I can always approximate f, such that, and this is the main point, that this Fn approximate in H2 the function f. Okay. So right, this is the straightforward point. So actually we have now constructed, and then we will like keep going out. So we have to construct the stress integral at, if we integrate always up to the terminal line t. And second thing we have as well is we can extend Ito's isometry. This will be very useful. This is the content of lemma 3.6, which is Ito's isometry, which tells us that if you have a function f in H2, we have that the H2 norm of f is equal to the L2 norm of the integral of f. Right. Okay, and I mean this is not so hard because it's just an extension of the E2 isometry, the simpler one. So let me give you quickly the proof. So let us consider a sequence Fn, which is in H2 0, so it's a sequence of simple functions such that f minus Fn goes to 0 in the H2 norm. Okay. Okay. Then, I mean, this is just by the definition. We know that the integral of f, or as it is defined, goes to 0 minus the integral of f n goes to 0 in the L2 norm. Okay. And this means, or what do we get? So if I look at the norm of f in H2, this is nothing else than the limit of n to infinity of the approximating sequence, right? This is how we choose Fn in H2. Here we can apply the Ito isometry in its simple form. Simple version, which tells us this is nothing else than the limit of n to infinity of h of the integral operator of Fn in L2. And this is nothing else than the L2 norm of the integral of f. Right? Let me also make this, give this a red box. This is all we wanted to prove. This is our Ito isometry. Okay, here we go. And in the next video, we will extend the integral operator, which is currently defined always from 0 to capital T to really to be a stochastic process running in time. Thank you very much for watching the video.